In this video, we're going to talk about molecular orbital theory in regards to the p orbitals. When we have atoms like dinitrogen, they have their two s orbitals and they also have their two p orbitals. So if I had a second nitrogen, I'd have its 2s and its 2p's. In terms of the energetics, to scale we can adjust it, but basically the s orbitals tend to be well below the p orbitals. This is true not just for dinitrogen, this is true for dioxygen or difluorine, dichlorine, dibromine. Let's do difluorine for this part here. Well, you're going to go down in energy when you overlap your s orbitals constructively. So we have a sphere, we get our double sphere with them in phase. This is sigma, and it's bonding. And you get your anti-bonding, where they are out of phase. And so you end up with a node down the middle. Well, this one was sigma star, sigma antibonding. And this holds true even when doing this with fluorines, not just hydrogens and heliums. There's s orbitals in the valence and they will interact. Let's talk about the p's. Because what kind of p's do I have? I have an up and down, I have an in and out, and I have a left and a right. When I bring these together, well, there's two types of interaction. I can have end-on-end interaction, which would be sigma, or I could have side-to-side interaction, which would be pi. Two of these, the in and out and the up and down, because of their directions, are side by side, but the left and right, that is going to result in a sigma interaction. Sigma interactions are stronger. They overlap more, they have greater influence. As a result, they go farther down in energy. Our sigma bonding, which would be negative outside, positive inside for one, and positive inside, negative outside for the other, this is going to create a shape that has a much greater density in the middle. And so you'd end up with something with a bunch of positive here and a little negative on either side. As my left and right p orbitals interact, they will have a much greater effect than my up and down and in and out. This is a sigma interaction, and it's bonding when they're in phase in the center. My pi orbitals, I get two sets. We get the up and down, as we said, and the in and the out. What does that end up looking like? Well, effectively, I've got a nucleus, and you get a bulb on top, and you get a bulb on bottom. One is plus and one is minus. And you can do that for the in and outs as well. It's a little harder to draw. But again, one's plus and one is minus. That is, you're lining up those phases. So if we draw it like we had seen it, this would have been plus and plus, minus and minus. They were in phase, and so there's still a density towards the middle pulling the two nuclei together. It's a little above and below the center line, but it's still in the middle between the two nuclei. This is a pi interaction, though. It's not as strong, and so we don't go down in energy as well. They're not as strongly overlapping, they're not as strongly attracted, so they don't decrease in energy versus the atomic orbital as much as our sigma bond did. But that also means when they're out of phase, they don't go up as much. If I have an up and down, plus minus, minus plus, well, they're going to destroy each other in the middle. I'm going to end up with a node. What's that going to look like? Well, effectively, I've got to have my node and I have my nuclei. And there's an above and below, but they go away from the center, so it's going to look like this. Plus minus on top, minus plus on bottom. And there's two of these. There's also the in and the out. As a result, by canceling in the middle, most of my density is on the outside edge, pulling my atoms apart. This is a pi antibonding. Anti-pi is not cake, it is just antibonding. Well, our last set of overlaps then is, let's look at those p orbitals. If I have them plus minus and the next one is also plus minus, they will cancel in the center. I'll have a node, I'll have a big plus and a little minus, and I'll have a little plus and a big minus. Most of that density is on the far outside edge, and so it is pulling them apart a lot. This is a sigma star, sigma antibonding. When p orbitals interact to form molecular orbitals, this is the forms that they create. This gives us a pattern, though, and it is a fairly consistent pattern, though we will learn a little modification when we get to mixing. But effectively, I end up with a sigma and a sigma star from my S's. I then get another sigma from my P's. I get two pi's. I get two anti-pi. I get one anti-sigma. This filling pattern is the general filling pattern for molecular orbital diagrams. Now, it's especially true for the dimers we've been working with. If you want to go to more complex molecules, it can get a little deeper, but we're going to stick with dimers of things, or two atom systems. So this pattern, much like 1s, 2s, 2p, 3s was generally conserved, this is generally conserved. So whatever you're given is pretty much going to look like this, with a few rare exceptions when we talk about mixing. Well, this pattern lets us explore differences between molecules. So let's look at N2. Well, nitrogen, each nitrogen has 5 electrons in its valence. So if you drew it, you'd have this for your Lewis structure. The valence electrons that come in from each nitrogen are 5. So you would have had some 2s and it would have had 2 electrons. You would have had some 2p and it would have had 3 electrons. And each of your nitrogens would look like that. And so as they went to fill your orbitals, well, 1, 2, 3, 4, you get your p orbitals, 5, 6, your pi orbitals, 7, 8, 9, 10. We can just fill our general pattern this way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Whether we draw it out in that full bringing 2 nitrogen atoms together path over here, or we just recognize that the center is generally going to look like this. The nitrogen, in another video you will see, it mixes and it looks slightly different. But we can follow this general idea. What if we wanted to do it for dioxygen? Well, dioxygen just has 1 more electron on each of these. Well, I filled these lower ones. The next orbitals are my pi antibonding. So those 2 extra electrons are just going to go there. We expect each oxygen to have 6 electrons. There's 2 oxygens, so there should be 12 electrons to make MOs out of. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Dioxygen has unpaired electrons in the MO theory. Remember that, like p orbitals, equivalent orbitals spread the electrons out before pairing them. My pi orbitals are equivalent in energy. We call them degenerate. But because they are the same energy, it is easier to spread electrons out than to pair them, and so they will spread out first. The result is I have unpaired electrons. My Lewis structures can't show me that, my hybrid orbitals can't show me that, but my MO theory predicts that it should have unpaired electrons. This is why dioxygen is paramagnetic. It has two more than nitrogen. Nitrogen's, remember, paired up at just the pi orbitals. They were all paired. Dinitrogen was diamagnetic. Dioxygen is paramagnetic. If you continue this to F2, well, fluorine would have one more electron on each, and so you would fill those in to your remaining open spots on your pi. Each of these should have 7 electrons times 2 for 14. 2, 4, 6, 8, 10, 12, 14. F2 should be diamagnetic, and it is. If you were foolish enough to pour liquid difluorine across the magnet, you would notice that it didn't stick. It probably would have violently exploded and killed everybody. Don't mess with fluorine. But it's not paramagnetic. It is diamagnetic. So our molecular orbital theory, now that we can apply the p orbitals as well, let's just see why we expect dioxygen to have the property it does. Our hybrid theory couldn't explain it. Our Lewis structure VSEPR theories can't explain it. But it is a lot more work to build and develop a molecular orbital theory. This is just for 2 atoms. If you want to include 3 or 4 or 50, it takes supercomputers. Now, you can kind of do a 3 or 4 by hand. But the idea is it's very difficult. And if you want to get to the farthest, most advanced quantum field theories, it definitely takes supercomputers. So Lewis structure, VSEPR theory, hybrid theory, they're not perfectly accurate, but they do give us the right idea the vast majority of the time. And so even in modern research papers, we will talk about the S and P character, how S and P something is. Is it SP, SP2, SP3? Occasionally we'll say, it's like SP2.5 because, it's really looking like a molecular orbital theory. But it is easier to talk about it that way than it is to talk about it as an MO most of the time. And so these are different levels of theory so that we can answer what we need to answer in a reasonable time and to a reasonable accuracy.